Our textbook covers this topic in two different sections. Uh, well, depending on where you took Calc 1, again, it might be possible that you learn the El Hopito tool in Calculus 1, and some other places we learn it, like we learn it here in Calc 2. So, and let's do an actual review of what limits are. You know, those limits that you learned uh, back in Calc 1. Like the basic one where you just do the replacement theorem, how that works, you know, so all the different cases. So when we have a limit that when we try direct substitution and we get a number over infinity, it's possible to get either positive infinity or negative infinity for that function. And in this case, well, we need to essentially have a look at the graph to see the behavior of the function, and so we can get the actual answer. For example, limit of 4 over x minus 3 quantity squared. So if we graph this function, it's going to look like this. So a vertical asymptote at x equals to 3. And in this case, a pattern that you may have learned in pre-calculus is that whenever you have an even power for the factor that gives the asymptote, in this case, both go to the same infinity. I suppose that when you have 1 over x minus 3, for example, to the first power or to the third power or to the fifth power, in that case, we have different infinities. We have the different ones. So what I'm trying to say is this. In general, f of x equals 1 over x minus some value c to the odd, and f of x equals to 1 over x minus c to the even. The graphs are going to look like this. So let's say the asymptote is c over here, and as opposed to the even powers. Point for the odd powers, they both point to different infinities, as opposed for the even ones, they both point towards the same infinity. So that's a very important aspect from limits and behavior functions when it comes to finding limits. And in this case, well, they're asking for limit as x approaches 3. So recall that in this case, if we want the limit approaching 3, we need to look at both sides of the limit. The limit approaching 3 from the left and approaching 3 from the right. If both limits agree to the same value, well, that whatever that value is, that's our limit. And in this case, well, from either side, both point to positive infinity, so that's simply infinity. All right? And what else? Okay, another case, when we get a number divided by infinity, well, that's 0 because any number, any finite number divided by infinity is going to be 0. And in this case, well, that's 4 over e to the infinity, which is 4 over infinity, and that equals 0. And then the other two cases, whenever we have the first indeterminate form, which is the 0 over 0, the limit still exists, and in this case, that's where we use our algebra skills. You might remember that from Calc 1, all the factoring techniques, all the rationalizing numerators and denominators, multiplying numerator and denominator by a conjugate, what else? Trigonometric conjugates, what else? Simplifying a complex fraction, so that's where, so you might remember that from Calc 1, right? So that's the strategy that we take, and while the other indeterminate form is infinity over infinity whenever the numerator and denominator Our polynomials, we can use the way shortcut. They're not really shortcuts from pre-calculus. That when we have polynomial over polynomial and the degrees are the same, we just go with the ratio of the leading coefficient. Degree in the denominator is larger than that in the numerator, the limit is 0. And then the degree in the numerator is larger than that in the denominator, there's no limit. Essentially, it's infinity. Okay? So let's see. Let's have a look at these ones. A couple of examples here. Limit x as x approaches 3 of x squared plus 5x minus 24 and divided by x squared plus 9. So the first thing we try every time we have a limit exercise is substitute the value, and hopefully we're lucky to get a final answer. That's the limit. But otherwise, if you get a 0 over 0 or an infinity over infinity, well, we need our algebra skills here. All right? So let's see. Let's plug in 3 here. So that's going to be so 3 squared plus 5 times 3 minus 24 divided by 3 squared minus 9. Okay, so with the numerator we have a 3 squared, which is 9. 5 times 3, which is 15. 15 plus 9 isn't that a 24? Minus 24, that's a 0. And in the denominator, 3 squared, which is 9, minus 9, it's also 0. Well, this is good. Because even though we get an indeterminate form, we will be able to find its limit. So in this case, let's simplify the expression using algebra. So what about the numerator? So we will need to factor that in the numerator. How can we factor this one? So to factor x squared plus 5 minus plus 5x minus 24. X minus 3. X plus 8. And the denominator is a difference of squares. That's x plus 3 times x minus 3. And just divide out common factors, x minus 3, x minus 3. Limit x approaches 3 of x plus 8 over x plus 3. And all we do from here is, again, the substitution rule. Hopefully it works this time. So that's going to be 3 plus 8 over 3 plus 3. And nice, it works. 3 plus 8, that's 11. 3 plus 3 equals to 6. Questions about this one? All right, let's look at letter B. Well, letter B looks identical except for the value for which x is approaching to. So instead of approaching 3, this time it's approaching infinity. All right, so, well, in this case, what are we going to have? Of course, infinity squared minus 5 times infinity minus 24, that's simply going to be infinity. And infinity squared minus 9, that's not going to do any harm to the infinity. That's infinity over infinity. Okay, so let's see. There's a couple of ways. Number one, again, keep in mind that limits at infinity, what they tell us is the values of their horizontal asymptotes, right? What's the upper bounds for larger values of x, So that's one way to interpret them. And to compute them, number one is, which is the long way, it's by dividing every single term by x to the highest power that you see in the expression. That's going to take a while, and I think you already did a lot of those in Calc 1. And so in Calc 2, since you already did that, I would just focus on, I would do what we call, again, end behavior, and only focus on the leading terms. So because, again, it is actually the leading terms of the polynomials that determine the value of that expression, the ones that contribute most to the value. So really, the 5x minus 24 for large values are not really going to contribute a lot. So all we can do is simply limit x approaches infinity of x squared over x squared. Only focus on the leading terms. But what's x squared over x squared?
1.
That's simply 1. What's the limit of 1 as x approaches infinity?
1.
1. All right? So that's an example of a limit here. All right? Questions about this one? All right. El Hopito's rule. So again, some of you may have seen it before. Some of you may not have seen it before. We're going to go through all the details here, all the different indeterminate forms besides the 0 over 0 and the infinity over infinity. Well, and in this case, we need to work with a function that looks like a quotient. That way we can get those indeterminate forms. But there's other weird looking indeterminate form that you may not have seen, like 0 times infinity, 0 to the 0, 1 to the infinity, infinity to the 0, and infinity minus infinity. Well, in this case, we cannot subtract infinity minus infinity because we don't know which infinity is bigger than the other, right? So we can't do that. So we need to treat the expression in a different way. All right, so what's the El Hopito's rule? So the thing is that if we get 0 over 0 or infinity over infinity, then what we do is take the derivative of the numerator in the limit expression and the derivative of the denominator in the limit expression. And you need to be very, very careful because a very common mistake I've seen for this, note, this is not the quotient rule. It's only the derivative of the numerator divided by the derivative of the denominator, not the quotient rule. All right, so let's see. Let's evaluate each limit. Okay, so let's evaluate limit 3x squared plus 6x minus 1 over 5 minus 2x squared. So if we plug it in infinity, well, where is this going to go to? So that's going to be infinity over infinity, all right? That means we can use the El Hopito's rule. And El Hopito's rule means to differentiate numerator, the derivative of the numerator just using the general power rule. That's a 6x plus 6 divided by negative 4x. And then let's try direct substitution again. That is, evaluate at infinity. And that's going to give us an infinity over infinity. All right? So that means we can use El Hopito's rule one second time. So the derivative of 6x plus 6, that's a 6 over negative 4, which can be reduced to negative 3 halves. And the limit of that value as x approaches infinity, that's simply the value, negative 3 halves. And of course, I mean, we could have just used the end behavior from asymptotics from pre-calculus, because if you look at the coefficients, isn't it 3 and negative 2 for the leading coefficients? That's another way to look at it. Let's do one more example. Okay, so limit of 4x over e to the 2x minus 1 as x approaches 0. All right, so using direct substitution, what do we get? 4 times 0, which is a 0 in the numerator, and e to the 2 times 0, which is e to the 0 is 1, minus 1, that's also a 0. So we're good. Let's take the derivative of the numerator. Let's take the derivative of the denominator. So that's the limit of 4 over 2 e to the 2x. Okay, let's see if it works this time. X approaches 0. And indeed it works, I believe. Actually, let's simplify 4 over 2. That's a 2 in the numerator, e to the 2x in the denominator, and that's 2 over e to the 2 times 0, which in this case 2 times 0 is 0, but e to the 0 is simply 1. 2 over 1 is 2. Right? Let's do one more. Letter C. Let's see if we have an indeterminate form. So ln of infinity, where is ln going when x is infinity?
0.
So, okay, let's think of the graph of ln of x. Recall that the graph of ln of x has an x-intercept at 1, 0, has the vertical asymptote at the y-axis, and it goes like this. All right? So where is it going for large values of x? Infinity. I know, it's steeper for smaller values and less steeper for large values, but of course that looks like it's going to infinity. All right, so, and e to the infinity, of course, infinity. Okay, so this is good. And by the way, just a little bit on notation. Every time we use the Hopito's rule, it's important to denote that we are using. So let's just use LH to denote that we use the Hopito's rule. This one just once. Okay, so let's do Hopito's. Okay, what's the derivative of ln x? 1 over x. And what's the derivative of e to the x? E to the x itself. Okay, let's rewrite this 1 over x times e to the x. That's going to be limit of 1 over x e to the x. X approaches infinity. No, this is no more Hopito's. I'm just rewriting it in an easier way to visualize. Well, what's the limit here? We agree, 0. Infinity times e to the infinity in the denominator, even bigger infinity, so we are good in here. And guys, I would like to stop here. We're gonna take it from here next time.